Hello, everyone. My name is Mehdi. I'm from Fujitsu Research America. We have research in Europe, and also we have in India and Japan. Currently, we do have the also demo of this system, which I'm going to present here. So hopefully, we give you some idea about this. The title is a Generative AutoML for Tabular data. So So mainly, if we look at the why we need actually AutoML. So currently, the different platform exists, and it shows that if you want to do the machine learning, especially for the tabular data, you have to try the different models. You have to try different feature engineering, data engineering, in order to have a best performance model. Sometimes it's come with a specific data scientist activity, how much mature the data scientist can do the job. So then the performance might be improved or decreased, right? So that's a problem. So we want to do the whole things based on automation. So, but when we want to look at the automation, we need to have a generative AutoML approach, which means we can tackle the different data set, diverse data set, different type of data, and then we want to generate the pipeline and then execute the whole process and get the best performance. In compared to your exploratory approach, you try this or that, and then it doesn't work, or you want to improve it, then you try something else, right? Another one is we want to look at those diverse data set. That's an important factor because sometimes you shift the domain from one specific domain to another domain, then you will end up with completely different model, different pipeline you need to generate. So that's we want to target also to reduce the cost. So then, and also we want to look at the, we want to establish a platform that you will be able to run on your own infrastructure or you want to run on the cloud. And also we want to look at if there is any possibility we can do the decision making, and we want to see what is the decision maker, how we select the decision, how much we confidence about each decision to interpret it. So, and then we want to define open ecosystem. So there is a bunch of open source library exists, but sometimes when you use the AutoML platforms, you mainly rely on a specific provider and you lock in. So we want to avoid these issues, right? So in order to do that, we are interested in looking to first dramatic reduction of the computation time as well as how much effort they need data scientists to work on the pipeline generation and model selection. So in order to do that, we look at two different categories of the users. One category is expert users that they knows what they are doing. They can run the code, they can execute the code, they are flexible, they can select the model, they can update the model, they can update the feature engineering, data engineering. And also some users, they are beginner. They don't basically care about the code. They want to see the model. They want to see the performance, right? So how we can deal with these two categories? So basically, once we want to look at no programming is required for the first category. And then we need to also reduce the effort of the trial error. We want to minimize those trial error. That's expensive because sometimes you have to pay for the cost for the storage. You have to pay additional for the pipeline generation. You have to pay additional for execution of the pipeline, which is the try. And then we want to reduce this cost. And another one is freely customizable. So which means we want to allow to the user to be able to customize the code. So we recommend some code, we recommend some pipeline, and then the data scientist or user can be able to update those code and customize it. So in order to do that, we introduced the AutoML platform that basically you look at the tabular data on the left-hand side. You can see some tabular data. It could be any type of tabular data input, like a JSON, CSV file, or any type of stream data. And then you want to look at, generate the pipeline, and add the explanation and the code. So that's include the feature engineering, data engineering, model selection, and all the process until you deploy the whole model on the server. So why we want to look at the tabular data? So tabular data is one of the popular content actually across diverse industry we are using, including the different databases, including the rational database, no rational databases, NoSQL databases, all the different category of the data set. We basically look at those content. We want to predict some values, or we want to have some regression or classification problem on that. So that will be target, finance, medicine, and on diverse data sets. So what type of data set we are talking? This is one example that shows, for example, heart disease data set that we want to, for example, look at, predict the diagnosis of the heart disease. We want to see, for example, the different classes, and we want to predict the values. So there is some features. Here is a clear table we have, like the tabular data and everything clean and numerical representation, right? But it doesn't work always. So in another data set, let's say, for example, bank marketing data set, it's include a set of the values that they want to predict this customer should be selected or not, right? So in this data set, you will see a category feature, numerical representation. So it's a mixed value. Sometimes this mixed value is challenging. Sometimes you have to replace this mixed value, for example, numerical representation or categorical. How you should decide, you should go move everything to numerical, or everything should move to the categorical features. Sometimes you can see, for example, it does have categorical features, and you want to sort the value based on those categorical semantic orders. So those are all challenging in this tabular data set. You look at, for example, internet advertisement. So you want to predict this is the image or this is the advertisement image. So in this feature, you look at the different set of the values. Some value is missing. So how we should replace those values? Should we get some average, replace that? How we should do that? Should we replace it with some specific value, or just ignore those rows, right? Observation. So that's always challenging for data scientists. They try to address these issues. So this is another one. For example, there is a sparse value, so then exists in this data set. So you have to understand how you should deal with these sparse values. So data scientists, they try to address this one by trying a different approach. So if you look at, for example, in the Kaggle community, you will see, for example, some people get a very high rank in model prediction, a specific task, and then they come up with very good performance model. But actually the reason because they did just try out. So we want to avoid the try and error. So all of them are challenging. So diversity we have across the different data sets. We have missing values, we have a text embedding, categorical encoding, sparse data, mixed types. So all of them is challenging in tabular data. So how we should address this one? And in addition on the top of these challenges, we are also dealing with another metric that including the explainability, including interpretability. We want to interpret why we decide this decision. And we need to explain that, those decisions, how we make those decisions, why we make this decision. What was our confidence level, right? And if we did this decision, what is alternative option would be? What would be alternative pipeline? What would be alternative model selection? So all those metrics are important factors. Another one is the flexibility. So we want to allow the data scientists to actually customize the code so they can do based on customization of the code or model selection, so even they can improve further. Even, for example, AutoML can be used as a start warm-up. So it's initiating some pipeline, and then you can improve those performance. So how we should deal with that? So this is our proposed approach. So in a supervised setting, we basically will look at a function that does have take one input, that's given input data set, and we want to generate machine learning pipelines. So these machine learning pipelines, let's say we want to look at the data set further, we'll look at the metadata of the data set. Later, I will explain some example how it looks like the metadata of the data set. So then we look at this D as a given input meta feature of the data set, right? So now we're going to look at across the different data sets, we want to learn those meta features. But when we look at the different meta feature, we're actually looking to minimize the loss function across diverse data sets, which is across the metadata test data set, and where we have a file, I define a function of the theta, where the theta is a parameter to decide how we adjust these values to find the best model. That's a run on the metadata trained data set. So how we should do this process? Across the different diverse data set, we want to find the best model. So first, we look at the corpus preparation. In the corpus preparation, first we generate a set of pair of data set and code. So which means we have a code for each specific data set. And we are tackling diverse data sets. So once we have this data set prepared, and then we look at the functions we call denoise and augmentation, which basically label the data that include labeling the tabular data. We also labeling the code itself that corresponds to a specific data set. So that would be applied to a multiple different, let's call it project, right? That diverse data set. So then we have the data set, and each one does have the pipeline generated for a specific one. So then we look at that, we build each one, and we execute that. So some of the code might not executable, right? So those we should ignore that in this case to have a more precise answer. So we execute those pipeline on a specific data sets. It can be generated, for example, we can collect from diverse pipeline exists, or we could possibly, for example, generate synthesizers. So now when we look at the model selection, there is a different approach to tackle the tabular data to select the model itself. So there is a couple papers that indicate that deep learnings not always perform very well on tabular data. Especially, for example, in the recent paper in Neurops that explained that the tree-based how perform better in compared to those deep learning. And then, interestingly, that performance, not only the matter, is also computation time. So let's say you have an AutoML, you run the AutoML for 1 hour, it costs you, for example, $1,000 on your data set, right? Because you have to purchase the server that costs you to save the storage, and you have to run the server. So all those information that you process for 1 hour, it costs you. So then if you use the different approach, different model, and then you come up with lower performance, is actually you lost those money. So back to the meta features extraction. So meta feature extraction, we look at the data set, and we collect the information, And it's include a dataset feature, that number of rows, feature, target. For example, missing entries, feature types, those are some examples. For instance, measure of the symmetries. We look at the skewness of the data, we look at the cortices, we want to see what is the distribution of the data, how looks like the data in tabular data. So once we figure out the metadata of this tabular data, then we look at the diverse set of the data sets. So now we collect the measure, for example, distribution and et cetera from the tabular data. So we call it meta feature extraction. The next step is pipeline labeling. So from one side, we have a pair of the code and data set, right? So now from the other side, we're going to label the source code that correspond to a specific data set. So in the labeling, we use the big supervision to annotate the values. So for instance, we can look at, say, okay, this is a load data that include, for example, a set of lines that correspond to loading the data. So we can do the same process, for example, for model selection. We could do the same thing for inverse, for example, target, that a specific feature engineering that done on target or done on a specific columns. So we do this process, and we call it big supervision based on this labeling of the pipelines. So now we collect those information. Now what we can do with that? So now next step is train the model across the different data sets based on the test data set, and we want to look at the loss function and minimize the loss function across all the different data sets. So while using their training, we call it a skeleton prediction. So it's going to say, okay, this one more likely now you need to do the function like an encoder. You need to encode this value. You need to impute this missing value. You need to do this process. So all those features, part of the skeleton, will be predicted. But it doesn't have the order. So now next step, we look at the order. We look at to understand what is the order. What would be the order for each specific feature that we train? So we capture those order from the component order relation. And now we generate a set of candidate pipeline. Candidate pipeline is actually executable source code that twists different type of feature engineering, data engineering, and model selection, and it comes up with final output. So then we need to interpret those values, and we look at the accuracy check, and then we look at what's the optimal machine learning pipeline. So in this step, we're not going to execute 1,000 pipeline generated. You have AutoML, for example, you want to just save time. You want to execute only top 3 that recommended sorted value initially, and then you're going to select the specific, let's say, top 3. And then based on top 3, it tells you what is the top one from this top 3, the best model. And then it's going to add the pipeline explanation based on the model, because we already, during the training, we understand what is the theta. That theta actually how data scientists try to adjust the pipeline, customize it to improve the performance. So those theta can give us explanation. So how we do that? So we call it pipeline explanatory, that explain first data itself. So tell us what type of data we have actually. And then the next step, explain the generated pipeline, what type of pipeline we do generated, and explain each line by line, as well as explain the whole block of the pipeline. And explain why a pipeline is generated, why is select, what is the confidence level on that. So to generate the confidence level, we can look at the theta parameter, because when we train the model, we understand those theta or generate a set of confidence level for threshold for a specific task when we want to select for the pipeline. So then we look at take advantage of the external resources, for example, use the BERT language model to use those contexts to customize the summary and adjust the explanation and generate the output. So let me show you a demo. how it looks like. So basically, the demo, we're going to show how the system actually performs. If there would be any issues, so more likely, it doesn't show still. Okay. So basically, we load the data set, we load the tabular data, so it's already, the model already trained based on the data set which we collect and based on the approach which I explained. So now, once we have the tabular data, we're going to select the tabular data as an input. So once we select the tabular data as an input, then it's going to look at the tabular data, generate the meta feature, and fit into the model. And then once we have the meta feature, we look at what type of data set we are looking, what type of meta pipeline more likely we can generate. So then it's going to basically load those most likely pipeline and sort those as skeleton, and then generate the new pipeline and show for example, if we select the top 3, it's going to show the top 3 models. Once it shows the top 3 models, then it tells you what is the top performer. And then once it shows the leaderboard and you see the top performer, then it's going to show you all the explanation for a specific data set, and as well as for are you able to play that? All right. So anyway, so feel free to stop by the table. We have the live demo, so you will be able to try yourself. On the back, my colleagues, they are there, ready. So maybe I can just show those as screenshot. The video doesn't work, so unfortunately. So let's see. So first, it's going to, even the animation here doesn't work as well. All right. All right, so first we submit the data, is generated. So I'm going to just point out, so those highlighted doesn't work. So first we have generated the pipelines. It's going to tell you what is the pipeline and the leaderboards. And then it's going to tell you, for example, what is the pipeline number 2, number 1, and the performance. And then select the top performer, and then once you click on the, for example, let's say Jupyter Notebook, it generates also both Python code as well as Jupyter Notebook. Once it's done, all right, so at least this one works. So once it's done, then it's going to explain, for example, all the data set, what is the data set, including the EDA. So it shows, for example, in this case, shows the data set is Titanic data set, include 12, for example, columns, in this number of rows, and then shows how it looks like the data set, and then it's going to say, for example, how many null value we do have, and then explain those data. And then the other feature, for example, for each pipeline generated for each block is going to have an explanation. For example, say, okay, this is going to remove the missing values, and using these features, and then explain that, why select this pipeline feature engineering, and then explain that what is the confidence level for that. For example, it's 30%, and based on this threshold, for example, say, based on 50% threshold, it was expected. Now, currently, I can see from this data set is more than 50, is a 60%. That's the reason I decide this feature engineering. Similarly, it can apply to any pipeline as well as for the model selection. For example, it can show that what is the top performer model. It's also on the left-hand side, you can see the probability that shows that what is the probability of the model. And on the right-hand side, because we select the top 3 rather than for example, top 10, from top 10 of the selected pipeline, then it's going to tell you only 3 of them is executed, and it shows that performance. So then it's going to shows you the list of the selection and the top performer. So in summary, basically we're looking into the what is the efficient way to generate the pipeline that we want to avoid the exploratory approach. We don't want to try and different number of the pipeline, highly number of the pipeline to generate and see what is the best performer. So by using this approach, we're going to minimize the cost and as well as for the time that we can predict and generate the pipeline. The next one, we also show that this does have a high accuracy in compared to other existing AutoML platforms. We also generate the code. And also, the other platform have a limited explanation in terms of, for example, what is the pipeline, what is the model, but we actually explain that each pipeline, step by step, what is the parameter, what was the threshold, and why is past those thresholds. And as well as produce only, some other platform produce only machine learning models, but they don't allow you to see what actually source code is it, how is generated, so it doesn't have. But we actually use the open source tools, so you will be able actually execute on your environment, on your machine even, if you want, or you can run on the Docker file, so that's existing approach. And also, for example, some other platforms that allow you to execute, for example, tell you the model, or another level that tell you API level access to your model, so it doesn't give you actually the pipeline. It gives you the API level access so you can execute and repeat again the process. But still you rely on the platform. So we're going to look at the platform independent. Thank you so much. Please check out live version of this demo. Hopefully, so this doesn't work, sorry about that. But my colleagues on the back, they are open, so feel free to stop by, look at the demo. You can select a different play around and then select the a specific, for example, data set, as well as what we show here is a UI prototype, but it's actually SDK-based available, so you can use the SDK or web-based currently. And it's, if you have a startup or if you are a data scientist, you want to try the different data set, feel free to contact us as well. We can reach you and organize a demo for you. And also, if you are interested, we are hiring data scientists and researchers. Thank you.
Thank you, Mehdi. Do we have any questions? Right here.
Thank you for the great talk. I think it's more of a comment than a question. So the general AutoML, like most of the AutoML approaches, you mentioned that the problem is the cost, because now, like humans usually with the DNN models, they do the hyperparameter tuning, they do like select architecture, loss function, everything. Now, in this big search kind of world, now the machine is trying to do that. And I wanted to just mention that it's not just the cost that is concerning, it's also the carbon footprint that MIT had this really scary type of analysis of how much heat these building, like all these models will create. So it's very interesting that you are kind of limiting that search, but still, like, could you explain a little bit, basically, what is the trade-off between using this type of AutoML as efficient as it is to using humans to actually do that feature engineering and other things?
Sure, thank you so much for the comment. I completely agree with you. Actually, I should, we had a paper, I think 2 months ago in AutoML conference, co-located with ICML, and that paper actually highlighted in MIT Technology Review because the sustainability that we were looking, rather than we train everything, we use the zero-shot setting. So in terms of the exploratory, it's basically approach, as you say, mainly because it costs a lot of computation, and as you mentioned, pointing out, sorry, I missed that point to add to this slide, but that's very good you point out that. But mainly, what we do, for example, we generated 1,000, for example, pipeline, but we sorted based on the confidence level, based on what likely would be possibly this pipeline correspond to what you want. This is one a specific task. Actually, when you select in the setting, you will have an option in advanced setting or in SDK to select, for example, say, I want to use only 5 top confident level, for example, selected, and then those executed, and then come up with the best model. So it's try to keep balance between try and error and metadata-based feature prediction. That's a very good question. Thank you so much for pointing out. Yes?
My question is kind of maybe a refinement of that question. So even if your meta pipeline is linear, if you have a very fat data set, right, with lots and lots of features, the number of candidate pipelines can be like prohibitively large. So so in order to do these candidate selection, like do you do any kind of algorithms to kind of maybe some genetic algorithm or something like that to kind of select, effectively select the candidates?
Yes, yes. Actually, during the training, we do the mutation. So to understand what would be the different pipeline, different structure, different skeleton would be actually performed. So rather than the data scientists try to figure out those mutation by hand, data set by data set, we already done during the training. And then when you do that during the prediction, you're actually just saving your time, your cost, because one time we done that, you don't need to do the repeat again that process.
You're not exhaustively searching the full space, right? So you're doing efficient, so
sure.
that kind of answers partially the earlier question too. Okay, very cool, thank you.
But basically, we look at the high probability, and what would be the more likely those mutation would be helpful. Yes, that's very good question. Thanks.
Hello.
Yes.
Thanks for the talk. So in practice, for many of these machine learning tasks, most of the effort is focused on feature engineering, feature transformation. There's some kind of hyperparameter tuning or trying to choose a model. I'm just curious, like, for the system you build, like AutoML, does it handle, for example, category features, I want to do one hard coding, but then there's also numeric features, I do want to do some transformation. Sometimes even log transformation can actually improve the performance a lot. Can you share a little bit more, like whether or not your system can handle that, or like say, how do you handle that?
Yeah, that's a very good question. So basically, all those features exactly, if you look at, for example, in the cargo community, you will see, for example, there is people try this, try do, and then, for example, just simple one specific transformation of the data, you will be end up with best performer, as you point out. So there is a kind of what we do, we actually, as I said, rather than we do all the different possibilities, we do more likely what would be happen based on, for example, popularity on the related to the code and the data set, based on the relation between the metadata to the code. So then based on those corresponding and the likelihood of the process, then we're going to mutate and generate the pipeline, and then we look at the performance of those model. And then in terms of the, for example, let's say, for example, categorical encoder, it can find all the different possibility, and then it can, for example, if you provide those value and see more likely, for example, it's require imputation, or if you require categorical encoder, it do all the process, including the feature engineering. One of the related work is, for example, birth sort that we recently also published. You may take a look also, that shows that, for example, how we do the categorical encoder and then encode the values. Thank you so much. Any other question?
Great. Well, thank you very much, Mehdi.
Thank you.
Appreciate it.